Welcome. One of the great paradigms in computer science is the Unix philosophy: simplicity, generality, and clarity. And these three pillars also exist in geometry, finite geometry. I work with these three structures. Each has an advantage, each has also its limitations. So graphs, that's the most intuitive structure. It is also the oldest structure. It has been introduced already in the 18th century by Euler and then developed in the 19th century. And it's a very nice structure also if you are interested in higher dimensional spaces. The graph comes naturally with Simplicial complex, and that's the next structure. It's the simplest structure of all them. It has only one axiom. It's a finite set of non-empty sets closed under the operation of taking finite non-empty subsets. So it's 1907 was the birth date of this structure. It's very nice too, and every graph naturally defines a Simplicial complex. If you have an icosahedron, you can represent that with a skeleton. That's usually how you do that, but it's actually a two-dimensional sphere. It has a nice Simplicial complex structure generated by the triangles. So that's a finite set of sets, very nice structure. And then we have I only started to work with this seriously now since a little bit more than a year with delta sets, especially in the context of open sets. The complement of a Simplicial complex in a given Simplicial complex is an open set. Also here, a very nice structure. It's actually surprisingly little one has to change. I mean, most of the code I have for Simplicial complexes actually works already for delta sets. So I have here an example which we might look at. So just from the computer science point of view, so we have three different things. Each has an advantage. This is the most intuitive. It's also something you can see. You can see the graph. This is something which is probably it's just very simple. It's just a set of sets, finite set of sets, closed under the operation of taking finite non-empty subsets. You can take a finite set of sets and close it. It's a one-line code to close it, and then you get the set of sets closed under the operation of taking finite non-empty subsets. And then here also you can actually just work with sets of sets. There's this a little bit unfortunate name, multigraph. I don't like this, but it's just a finite set of sets. And you have face maps, DI, and so they have to satisfy one condition. Additionally, we have something like a dimension, which is an additional data structure which you need. So you need three things to work with the delta set. You need a set of sets, you need a matrix which encodes all these face maps, which I take always the Dirac operator, which encodes everything you need to know. And the last thing is the dimension, the interpretation of what each set, what the dimension of each set is. Especially useful then if you take products. And so these structures all have advantages. The delta set is a finite topos, so it's a generalization of the set of finite sets, which is also a topos, but it has more geometry. And geometry one can define as something which has a cohomology. Once you have a cohomology, then you can talk about geometry, because then you have also calculus. The D is D here is the exterior derivative, div grad curl. So all the calculus we have is, possible in any of these structures. So I worked for many years now with this in this graph theoretical setting. Always, of course, looked at this Simplicial complex. Then a couple of years ago, I moved more to the Simplicial complex alone, not really starting with the graph, because it has some advantages. Are usually smaller, and then in the context of open sets, or if you take quotients of you take like an orbifold, you take a manifold and you identify some points, then you get something like an orbifold. And this is here also product spaces. Product spaces have been looked at here. I mean, There was also Silber. Eilenberg and Silber actually worked in '53 on the problem also to look at product spaces. One of the problem here is if you take the Cartesian product of a simplicity complex, you don't have a simplicity complex anymore. What you get, however, is a delta set. So it's closed under products, it's closed under quotients, it's closed under, you take manifolds there, submanifolds, level sets. I actually wanted to talk about Lagrange here, which is a very nice thing. Once you have a notion of level sets, once you have a notion of critical points, you can also talk about the Lagrange equations. But here is a kind of an example just illustrating how the data structure looks like. So we start with maybe a graph. It's a great source for geometric objects. If you start with a graph, you can take a graph and then generate the simplicity complex, which is just a finite set of sets. And so here, if you have then a finite set of sets closed under the operation of taking finite non-empty subsets, these are closed sets, and you have a topology which has been introduced by Alexandrov, which is not how stuff like the Zariski topology in algebraic geometry, but it's actually giving the right connectivity properties. If you take a finite topology on a finite set, then it has to be non-Hausdorff to make sense. Every subset is both open and closed, so it's a completely disconnected set. So distance formulas don't work. But Alexandrov in the 30s worked on this, and this is a framework which works very nice. But then you have open sets. Open sets are just complements of closed sets. What you can do here, I just took actually here a star of an edge, and this is an open set. It's open because every set containing that edge is included, so it just includes these two triangles, not the boundary, but the two triangles and x, so it consists of three sets. And now one can look at the face maps, one can look at the Dirac operator, one can look at the Hodge Laplacian, one can look at the cohomology, and so it all works very well. Here, this is an illustration of something I've worked on for several weeks, especially last summer, about this fusion inequality. And so this fusion inequality is a theorem. Also, I pointed out there that we have actually kind of nice notions also of quotient. If you take G over K, K is a closed subset, you take G over K, and this is a quotient, and this can be identified with, can be seen as the one-point compactification of the open set here. It's a very nice framework because you don't need to rewrite anything if you want to compute the cohomology. So this is actually a very, very small sphere. One of the motivations also here is that the objects are rather small. If you are going around the merry-go-round here, you start with a graph, you produce a simplicity complex. That's trivial then here. That's just a reinterpretation. That it's kind of just a simplicity complex is a delta set, and then you take the barycentric refinement where the objects are the vertices are the points, or the sets, and you take kind of a notion of inclusion. You have a notion of inclusion that gives you then a connection. And so you go around, what happens when you go once around, you get the barycentric refinement. Maybe just an example here. If you start with a triangle, and then what you do is you end up with a barycentric refined triangle where every of the complete subgraphs is a new point, and then you connect two if one is containing the other. So, and then you go, and then you can do barycentric refinements here. So that's going around here, or switching here forth and back. You don't have to go through the delta set. So if you deal with graphs or simplicity complexes, you don't really need the delta sets. But as soon as you want to look at products, for example, you need a topos. You need a structure where you can take products, where you can take quotients, where you can take subsets. So this is a very nice kind of the ultimate, structure you want to have. But essentially, what I just wanted to point out today, it's essentially the same kind of complexity, and you can work with this very well. Okay, that's it for today.